Okay, let's start. So what did we discuss in the last session? We talked about arrays. Array is a data structure. It's a linear data structure. And I think we also discussed two concepts before, right? In data structures, one is sequence, another is a set. And array, lists, and all are examples for sequences. And sets we will see later. So can you differentiate between a sequence and a set? What's the difference? Sequence and a set. Both are collections. What's the
Is
difference?
a sequence sorted?
A sequence need not be sorted. An array need not be sorted.
A sequence is ordered.
A sequence is ordered, right? Ordered in the sense the first element, second element, third element, something like that, right? So 1, 2, 3 sequence is different from, okay, let me write that, right? So 1, 2, 3 sequence is different from 2, 1, 3, right? So these are different. But on the other hand, a set is an unordered collection. 1, 2, 3 is same as 2, 1, 3, right? They mean the same. It's just a bag of numbers, right? So here the order does not matter, but here the order matters. So now we are looking at sequences. In these sequences, we study arrays, we study lists, that is SLL, CLL, DLL, right? And dynamic arrays, all these things, right? Lists in general. All these are sequences. And you might have heard the concept called tuple, right? Tuples are sequences. Okay, what about sets? Set, can you give some data structures for representing sets?
No, hash set.
Hash set, right? Let's say hash table. Okay, next. Tree, right? All trees are sets. Okay, so see, so all these are sequences, all these are sets. So here, sets, we care about whether an element exists or not, right? Exists, relationship exists. If A exists in a set S, so if we want to perform this efficiently, or maybe union operations, intersection, and so on, sets would be the best data structures. So depending on the operations, you need to choose the data structures, okay? So first think about the operations. So what are the operations here? These data structures are not good for checking the existence of an element, right? So checking if a particular element exists or taking the union, intersection as efficiently. No, I mean, you can still perform them, but they are inefficient operations here. Then what's the advantage of sequences? I mean, we have some advantages. So suppose you want to quickly change the 7th element, right? That is possible using arrays. Or suppose you want to delete the last element, right? So that is possible if you use DLL. You can do this very quickly, right? So something like this. Okay, in O of 1 time, you can do all these operations. Again, depending on which data structure you're using. Arrays will have a couple of advantages and disadvantages. DLL has some advantages and disadvantages. Again, so here, depending on the operations, you can still choose which data structure you want. Okay, so this is the fundamental difference between sequences here and then sets. And you can also add more data structures like stacks and queues. So we will study about these later. Now, all these are kind of sequences. Okay? Order matters. Okay, let's get back. We were discussing about the array data structure. And so here the arrays are best for accessing the ith element or modifying the ith element and inserting an element at the last position, super fast, O of 1 operations. So in computer science, you can say O of 1 is same as theta of 1, right? And theta of 1 mean the same. Why? Yeah, I believe in computer science, you cannot have something like this, theta of 1 by n. Right? Prove me wrong. Probably you will get bonus points for it if you can prove me wrong here. So try to construct a program, right? Where when n increases, that is the input size, n increases, the runtime decreases like this, 1 by n or 1 by log n, something like that, right? So try to write a computer program that has, say, this complexity or say this complexity, log n, or anything that is decreasing. So all these are decreasing functions, right? Of course, they are asymptotically positive only, but they are decreasing functions, right? So try to construct computer programs like this. Probably you will not succeed. Prove me wrong and you will get bonus points for this. Okay, so that's why I believe O of 1 is exactly same as theta of 1 in computer science. In mathematics, that's not true, right? So if you just think about arbitrary functions, see, this function is included in O of 1, but this is not included in theta of 1. But in computer science, I'm not able to think about of a computer program that decreases runtime with respect to n. Okay, so yeah. Anyway, so let's come back to slow operations. Suppose you want to insert an element in the middle at the ith position, right? You take time. It's O of n. In the worst case, it can be n, right? So similarly, deleting, worst case, it can be n. And why? We already saw that using the scoreboard application, right? You saw that you had to move elements every now and then, right? Whenever you're inserting and deleting. In the best case, it was one shift, but in the worst case, it could be n shifts. So O of n. What about increasing size? Suppose you want to increase size. You cannot do it with a static array. The normal arrays are standard arrays are static arrays. You cannot increase the size of static arrays, right? So we could not. Later, we will see a concept called dynamic arrays where we can increase the size. But using static arrays in a different way, we think about dynamic arrays. Anyway, so to address all these disadvantages of arrays, right, we can come up with more data structures. Next, we will see singly linked list. So it solves it addresses some of the disadvantages of arrays, but it has its own disadvantages. Okay, SLL, singly linked list. See, it's a list. It is linked. A lot of nodes are linked singly. Singly means the direction, it's a single direction. You can go in a single direction. Okay, that's the meaning of singly linked list. Okay, let's see. So it is a linear sequence of nodes. Suppose you have a collection of airport codes, right? Something like this. LAX, MSP, ATL, BOS. So each node has a data and a pointer to the next node. So this has data and pointer to the next node, so on. The starting node is called the head node. The ending node, the last node, is called the tail node. So look at this. What happens? The tail node points to which other node? It points to a special value called null. Null means end, the end, right? Null is a special object in programming languages, right? Okay, so this is your singly linked list. Simple, right? It's a collection of nodes. Each node can be considered as a struct in C or C++, or a class. It can also have functions, right, in C++, Java, and all other object-oriented programming languages. So it has data and it has a pointer. And this data need not be integer, float, string only. It can be a record. It can be a person's record, right? With say 10 MB of data with a lot of information, right? It can point to a record with a lot of information. This need not be just one value. Okay, so let's proceed. So first we will define the node class, and then we will define the singly linked list class. And you see that a lot of nodes make a singly linked list, right? Okay, so node class is a private class. A private class. So anyway, so we will come to this later. It has element, it has the next pointer, and there is a constructor where you give the data, right, as well as initialize with the next point. Okay, and then you have get element to get data, get the next pointer, set the next pointer, right? Okay, that's it. And why do we have this as private? Why do we have this as private? So in object-oriented programming, there is something called encapsulation. So suppose this is your singly linked list. It's better to write node as a nested class, a private class that is accessible only inside this SLN. You don't want someone else to access this directly, right? Hence, node is considered as a nested class inside SLN. But you see a lot of textbooks where node is outside SLN. Ideally, that does not satisfy this pure concept of encapsulation in object-oriented programming, right? So suppose you have a car class, it's better to have the engine class inside the car class, right? So that nobody can, access this or change the values here, right? It's better to have this as a private class instead of a public class and outside. Okay, so that's the reason why we have it here. Okay. Now let's see the singly linked list class. So here is the class. Before that, let's summarize what we have, the methods we have. So every class is a collection of data and methods. We focus on methods because methods will have the logic, right, of how to use the data, how to change the data, how to use the data, so on. Okay, so here almost all classes will have this size, the number of elements, and is empty, whether the data structure is empty, right? Something like that. So very basic. Next, first, last. Get me the first element, get me the last element. That's it. Don't change them. So these are, you just want to access the first and last elements, but you don't want to change the data structure. And then you have add first, add last, remove first. That means these are update methods. These are access methods. You are just accessing, getting the information, not changing the information. So these are update methods. You are changing the data structure, right? Reading the data structure and changing the data structure. Adding a first element, right? E, or adding the element at the first position, adding an element at the last position, removing the first element, removing the last element. So here we have not shown removing the last element. You can have it, but later we will see that it is slow. If you have it, it is slow, but you can have it, right? You can have any number of functions. Okay. So here is your class. singly linked list, right? So what do we have here? So as I discussed earlier, so this is your SLL class. This is the node class. And it's better to write this as a private class inside SLL because you don't want someone else to mess with this information, right? Node class. Okay, so then you have the head pointer, sorry, head node as well as the tail node. As you saw in the previous example, right, of airport codes, SLL for that, you have the pointer to the first node, pointer to the last node, head pointer and tail pointer, head node, tail node. And then you have size, right? And then we have some constructors and access methods. These are very simple methods, right? Get the size, check whether the data structure is empty, get me the first element, get me the last element. And so here are the update methods, right? Very important methods, right? This defines the overall complexity of the data structure, right? Okay. Add first, add last, remove first. You can also add, remove last. Okay, look at the first and last methods of functions, right? Very simple. Go to the head node, get the element from the head node. Done. That's your first. Last method, go to the tail node and get the data from the tail node. That's it. If in case the list is empty, right, there is no first node or the last node, you will have to return a null object. That's it. Very simple, right? 1 or 2 line code. Okay, we will skip this. This is easy. Now, let's look at the basic functions. Insert at the head node. So you want to insert a new node just before head as the first node, right? So insert at first or add first really means this. So you have this SLL. This was your original singly linked list. You want to add a new node, and that new node is, say, LAX. So what you do is call that as newest, right? You can use any name. Let's call it newest node. The pointer, the next pointer of that newest node will be point to the head node, will point to the head node. And the reason is simple. You want to make sure that the new node is your first node, right? The new node is your first node. Hence, the next pointer of this newest node will point to head node. Then, okay, you added it now. Now you have a singly linked list. However, what you're storing in SLL is just the head pointer. If the head pointer points to this, you only have access to all these nodes. You can never access the newest node, right? Hence, you want to make sure the head node is updated. Now, you will assign newest to head. That means the head will point to the object that newest is pointing to. Now, this entire thing will be SLM. Entire thing is your singly linked list. So from here, you can start accessing all the nodes, right? You have inserted a new node just before head at the first position. Problem fixed. So any questions here? We will use a similar logic for insert at the end and deleting and all, but it's very similar to this. So do you have any questions? Okay, yes. Let's move to.
Professor, couple of questions not directly linked to this in the chat.
Yeah, sure. So we will talk about analysis later, right? Okay. Class recording. Yes, I will upload that. Okay, let's move to the code of it. So here is the algorithm. I mean, it does not contain all the information. Some corner cases are not covered in all these pseudocodes, but it has the logic, right? In most of these pseudocodes have the logic, but the complete reasoning is given in the Java program here. Okay, so let's see the pseudocode here. Nivest is the node, and that has this data E. Okay, you create a node. This is create node, and call it as Nivest. Nivest points to that node. Now, Nivest next will be the head pointer, right? Next, you will fix head. Head will point to Nivest. That's it. So that is a simple logic, right? Size is equal to size plus 1. The code is like this. So new node, the data is E, and the next pointer of that node is the head, right? Next pointer is the original head. Now head is equal to this. That means you are setting head to this Nivest node. See, all the logic is covered in this single one line. So this is powerful programming, right? See, whatever we wrote in 3 lines here is covered in 1 line, right? Node means this calling node. Nivest next is equal to head, that is already covered here, and head is equal to Nivest. Head is the new node, right? All these 3 lines is really in 1 line here. Okay, if size is equal to 0, tail is equal to head. So this is a corner case. Suppose the list is initially empty, right? There is no head, there is no tail. I mean, both are kind of null. You add one node, what happens? When there is only one node, head points to that node, tail points to the same node. So that's the idea. Tail is equal to head, right? Size plus. Okay. Can you tell me the complexity of this? What's the complexity?
We go about
Of 1, right? Just a constant number of instructions, right? There is no loop or any complicated operation here. O of 1. Next, insert an element at the tail. So here also the idea is simple. So you want to insert, right? So create a node, call it Nivest. You have the data, and the next pointer of Nivest will be null. And the reason is you are adding it at the last position. So, right? Okay. Then what do you do? Tail next is equal to Nivest. Does that work? Tail next was, so tail was this. Tail next was null. Now tail next will point to Nivest, right? Then you need to update tail. Tail will point to what? Tail dot next. Now this is your tail, right? That's what is shown here. Tail dot next is Nivest, and tail is equal to tail dot next. That's it. Make sense? You created a new node. You added it just after tail. So you will have to fix the pointers from tail and also the tail pointer. That's it, right? It's very similar to insert at first, but you are dealing with the tail pointer here. Okay, so Nivest is equal to node. Nivest next is null because it's the last node, so it has to point to null. Tail next is equal to Nivest, right? And tail, the node inserted at the last position, will automatically become the tail. So that's why tail is equal to Nivest. Size is equal to size plus 1. Done. Right? Okay, let's see the code here. Newest is equal to new node of E comma null. Right? The element is E. The first line here is this. The second line here is this. Right? Okay, next. So let's think about this. Let's consider this first. Tail dot set next is newest. What do you have here? Tail dot next, set next, same here, okay, is equal to newest, and then tail is equal to newest, right? Tail is equal to newest. So we have this logic, the same logic. What about this corner case? Let's think about it for a moment, right? Suppose there is no list and you want to add a node. Suppose you added that node. What happens? Head is your newest, tail is your newest, right? Or you can say head and tail both point to newest. So head points to newest, tail points to newest if the list is initially empty. So that's a corner case, right? So apart from that, we have the logic here. Make sense? So does this make sense?
Yes.
Okay, so what is the complexity of insert a node at the last position?
O of n.
O of n,
O of 1.
O of 1, is it O of 1?
Yeah, since we have a tail pointer, we didn't have to traverse the linked list from the start.
Right. So it's a constant number of operations. It is not O of n, right? So we don't have a loop. Do we have a loop here? We don't have a loop. So it's not O of n. It's O of 1. Okay. Now let's suppose we did not have this variable called tail in our singly linked list. Suppose we do not have tail in our singly linked list. Suppose whenever you want tail, you have to access it from the head point or the head node. Now, can you tell me if you change this code with the condition that you don't have access to tail directly, you don't have the variable for tail, what will be the complexity of that new code segment?
Now it's O of n because you have to traverse the list.
Right. So when you cannot directly access tail, you have to start from your head node and keep on traversing the entire list, right, till you are at the last position, and then insert the new node there. So then you will have to make use of a while or a for loop, right? So that is O of n. Is it O of n or is it O of theta of n?
It would be, if you want to put it in the last position, it would be theta of n.
It is theta of n, right? So you don't you don't have the best case as 1 or log n, anything like that. So every time you want to insert a node at the last position, you have to traverse the entire list, right? The best case of that concept, the worst case of that concept, if there are n nodes, it is always n. So it is theta of n. You don't even need theta. Theta means constant times, upper bounded by constant times n, right? So here you know that it is exactly n. If you're assuming, right? Comparing or traversing as one unit. It is exact. You also know the constant factor. Theta of n is a better way of representation than O of n, because you know that it is exactly theta. But n is better way of representation than theta n, right? because you have more information, clearer information of what exactly is the number of computations or comparisons, right? So on. So it's just n. You can write it as theta of n. That's okay. Makes sense, right? Fine. So that's why just using one more variable tail, we could reduce the complexity of this add last to of 1. See, just one variable, if you delete that variable, this operation will become theta of n. Beautiful, right? With just one constant variable, you can reduce the complexity from theta of n to theta of 1. That's beautiful. So there can be situations where you will have to think about some variables to not do recomputations. I mean, a similar idea has been used in dynamic programming also. In dynamic programming, you will see that by using space to store the results of computations, you will avoid recomputations. See, tail, I mean, you can avoid that recomputation again and again. So even in dynamic programming, just by usage of the already computed results, you will not do recomputations. Hence, the exponential time complexity can be reduced to polynomial time complexity, right? So this is a beautiful concept. This is called space-time trade-off, right? Space-time trade-off. So sometimes if you think you can use a bit more space to reduce time, go ahead, right? So try to be open in that, right? Space-time trade-off. If you can use more space to reduce time, proceed. Okay. Next, remove an element at the head. So it's very similar to the previous one. Very simple idea here. You have a head node, right? Head is equal to head next. That's it. That's it. I mean, should we do anything else?
We have to reduce the size, right?
Reduce the size, yes. I mean, fix all those variables. But in the pointers, are we
should
doing
remove
anything else?
the previous head, set it to null.
You mean the previous head? See, head is equal to, suppose we do head is equal to, or say head is equal to head dot next or get next, whatever. And then, so suppose this is newest, right? You save this pointer, say the first node is head. Then what do you do?
Free the memory occupied by the first one.
Right. So can we say that free the memory for first? Okay, let's see. Is that what we are doing here? Let's think about it. Okay, so if head is equal to null, the list is empty, right? Else head is equal to head dot next. So I should have written this as else, right? Else. So if head is null, you cannot remove any element, right? Else head is equal to head dot next, size is equal to size minus 1. Okay. Look at the code here. Is empty, return null, because you cannot do anything. You cannot delete from an empty list. Okay. Head dot get element answer. Finally, you will be returning the answer. Maybe the user wants to use it, right? You're returning that answer. Head is equal to head dot get next. This is the core logic of removing the first element. Size minus minus. If size is equal to 0, tail is equal to null. And why do we have this corner case? Why do we have this corner case?
When there is only one element in the list.
when there is only one element, right? Now the head is you remove that node, the head is pointing to null. What about the tail? The tail is still pointing to the previous node, right? So hence you want to make sure the tail is also pointing to null, right? When there is only one element in the linked list, right? That's a corner case, right? So make sure you cover all these corner cases. So what are the corner cases? When the list is empty, right? When the list has, say, one node, when the list has two nodes. I mean, typically these three corner cases will be useful for all the functions, right? You don't need to worry about, further nodes. Typically it will be, one of these two. List is empty, list has one node, list has two nodes. Not only in arrays, in general, in the future, right? Whenever you are working with data structures, so you can say instead of list, if the data structure is empty, what do you need to do? If the data structure has one element, what do you need to do? If the data structure has two elements, what do you need to do? Right? So these are the corner cases. So maybe you need to apply some special logic here. So always take care of all these things, right? Else it will lead to bugs. Okay. Now let's get back to this. We do not have this concept of freeing the object. Can you tell me why? Why don't we have that logic here in our code?
Is it because nothing is pointing to it? And if nothing points to it, the garbage collector will get it?
Exactly. In the C programming language, there was no concept of garbage collection, right? So it was programmers' responsibility to free all the memory not utilized by the programmer, right? It was the programmer's headache to do, freeing all the memory so that the runtime can use it for something else. But in Java and maybe in the other programming languages also, you need to, study what they have, right? So this garbage collection, you do not need to worry about all the memory blocks that are not directly accessible by your data structure. Make sense? So does this make sense? All the memory blocks, maybe it is a node, maybe it is a hash set or whatever. If you don't have a direct access to that in the future version of your in the future instructions of your program, you don't need to worry about that. The garbage collector will take care of all those things, right? So that will eat up all these things when it tries to allocate more space for something else. Okay, so hence we do not need to worry about freeing space here. Make sense? So the best way to do it is setting, let me think about this. Oh, here we are not accessing this pointer, right? See, we shouldn't access this pointer, right? There shouldn't be any pointer to that object, right? Once, like, we don't have any pointer to that object. For example, when you do head is equal to head dot next, let's erase all these things. So suppose this was head, right? When you do head is equal to head dot next, now head pointer is here. You cannot access this in any way, right? So then the garbage collector will take care of all this. You don't need to worry about it. Okay. Now let's, here is one very important point about operations, complexities. Now, see, what did we did not cover here? Delete from last position, right? Suppose you implement delete from last position. What happens? Deleting the last node, removing the last node. Can you tell me what is the complexity of deleting the last node?
It's
Oh,
O
okay.
of 1 because you have the tail pointer.
O of 1?
If you
Okay.
have the tail pointer.
Yes, we have the tail pointer. What is the
Theta
complex?
of n,
Is it O of 1 or theta of n?
theta of n, because we'll have to visit till the last element, then only we can delete it.
No, but we already have the tail pointer, right?
Oh, so then it's
Oh.
it's theta of 1.
But
Not
the tail
O of 1.
pointer will be pointing to the null, I guess,
Yeah,
because
we can't go back
yeah, access it.
from tail.
Okay, see,
Cannot
the
go.
idea is, suppose you have this singly linked list. Suppose this is your tail pointer. I mean, tail node, tail pointer, whatever. You want to delete this. So if you delete this, you need to set the tail pointer to this node, the previous node. How do you come to this node? If you delete this node, how do you come to this node?
Well, you have to set tail. Oh, we don't have a previous. So then
Yes.
we don't have a previous. If we don't have a previous, then then it's going to be O of n because we have to traverse the list.
Is it O of n?
Theta then?
Yeah.
Theta of n. I mean, O of n is not incorrect, but we can say theta of n, theta of n is more correct, right? So here also, yeah, I mean, I could change this to theta of n, see, if you know for sure that you need to touch all the nodes, theta of n, right? Because you cannot directly access the node to the left of the tail node, right? One node previous to the tail node. So you need to start from the head and access it. So this is the headache, right? So deleting the last node takes theta of n time. What about all the other operations? I mean, whatever we have covered. O of 1, fantastic, right? But delete last is complicated because of this reason. You cannot access this previous node, right? Suppose we had access to that previous node using a doubly linked list, then what? Yes, then delete last is also O of 1. As this is not a doubly linked list, we cannot access it directly, right? We have to scan everything. So hence it is theta of n. Okay, next, increase size. In static arrays, we were not able to increase size, right? It was fixed, but now we can increase size. You have n elements, you can add one more element, so on, right? You can keep increasing them. And another beauty of SLL is, suppose in your computer, so these are the empty spots. Let's say these are the empty spots. Okay, suppose this is 1 KB, 1 KB, 1 KB, 1 KB. Suppose you want to create an array of size 2 KB, right? You cannot allocate this array. You cannot. That means you have 4 KB in memory, but you still cannot create an array of 2 KB. See? But in SLL, what's the beauty? You can create an SLL requiring 2 KB easily. What's the idea? When you create a node, right, it will allocate memory from here. When you create another node, okay, maybe it creates from here. Maybe third node, maybe it gets memory from here. Maybe it gets memory from here. So you get a chain of nodes like this, right? So this is, so the problem with array is you need to have contiguous memory on your computer, RAM, right? But here in SLL, that's not necessary, right? So even if your available memory is in pieces, it can allocate memory for these nodes in an arbitrary order, and they are linked like this, right? You can easily allocate to Kim. But the problem with SLL is that, see, it has to store element, it has to store the pointer. Pointer takes, I don't know, probably two bytes or 4 bytes, depending on maybe the bits, whether it is 32-bit, 64 bits, and so on, right? Maybe. So check this. How much memory does a pointer take? Is it 2 or 4, or depends on a lot of things like that, right? So the memory, there will be a memory increase for SLL, but still it will be able to get a lot of memory because of these things. But array requires continuous memory allocation, right? Okay, so that's related to memory. Let's come back. Access, modify. Suppose you want to access 10th element, right? It's not easy. In array, it was dead easy, but here you need to go to the 10th element from a starting point, right? Often. Insert at the 10th location, often. Delete from the 10th location, often, right? So on. Make sense? All these are fast operations, all these are slow operations. So if there is an application that says, you know, I will need insert it first, insert it last, and delete first, then you need to go for SLL, right? Do not go for array, because array insert first is theta of n, right? Next. Circularly linked list. So what is circularly linked list? So there are applications where we care for the cyclic order. So let's take a simple example. In operating system, you might have heard about process scheduling. In scheduling, there are 2 types, okay? Process scheduling, task scheduling. So we will see process scheduling here. There is another concept called task scheduling. Task scheduling you will encounter in parallel algorithms where there are multiple tasks. These tasks are allocated or assigned to different processors, multiple parallel processors. That is task scheduling. That's a different concept, okay? Process scheduling that you might have seen in operating system. We will see the diagram later, right? Round robin process scheduling. Multiplayer games. Suppose there are 5 players. The first player has a move, then the second player has a move, third player, fourth player, fifth player, and then again the first player, so on. It goes in a cyclic order. Or consider your buses and subways. They go in a loop, right? Maybe you want to process something, some data there in a continuous looping fashion, cyclic order, right? Okay, now let's consider this process scheduling, round robin process scheduling in operating systems. So how does this work? Suppose you have a list of processes here. Process 1, process 2, process 3, process 4, 5, 6. The CPU takes the first process, gives it some time, right? So maybe say 5 seconds. So after that, that P1 is put into this pool of processes. P1 goes from here and P1 goes at the last. Next, P2 is in the line. P2 gets 5 seconds. That is processed, and P2 comes here at the end. And this process repeats. So what do you see here? And this is called round robin scheduling. There are many types of scheduling. First come, first serve, shortest time, something like this. I mean, there are many types of scheduling. Round robin is one. in a cyclic order like this. Okay, so let's see. This can be implemented. If you want to implement this using a data structure, you can implement using SLL. Suppose that is called L. What do you need to do? So this is your singly linked list. Remove the first process from L, call it P. Now CPU will process P by giving it some time, say 5 seconds. After that, processing of P is over. Now P gets back into the queue at the end position, last position. So L dot add last of P. Right? So you have already removed it. Now you append that to the last. Next, you remove this, append it to the last, so on. Right? This is called round robin scheduling. And suppose you want to implement this, you can easily implement it using a singly linked list, right? Using these 3 steps. However, you can do better. Let's create a data structure called circularly linked list. And the idea here is very simple. So we will just change SLL slightly so that we can get a better data structure. Okay. And what are the changes? Suppose you had this SLL, singly linked list, right? You had the last node, you called it the tail node. Make sure that the next pointer of tail node points to the head node. Look at this. The next pointer in SLL, next pointer of tail node in SLL was pointing to null. But here, the next pointer of tail node will point to head, right? Tail dot next is equal to head. You just need one more operation like this. Okay, now this is the structure of your circularly linked list. And we will add one more method to it. Method or function. What is the function? Rotate function. It's fundamental, right? As you saw in round robin, you had to rotate it. Let's call it rotate. So instead of deleting from first, adding at last, multiple operations, right? We will define rotate method that does it in a very simple way, right? Give a time slice to process C dot first and then C dot rotate. It automatically deletes it and adds it. But we will not implement it like, deleting and adding. We will use some other operation to efficiently implement rotate. Okay, make sense? Okay, some optimizations, right? So we have 2 pointers here. One is the head node or head pointer and the tail pointer. But do we really need 2 pointers? No, we don't. Think about it. So when we have this data structure, we don't need this head pointer. Why? Tail pointer anyway points to tail. If you want the head node, just do tail dot get next. That will give you head, right? You don't need to save this variable. Saving that variable. Are we just saving one variable? I mean, it's no brainer, right? That's not a big deal. I mean, just saving one variable, who cares? It's not just about saving one variable. When you have a new variable, there are so many instructions to initialize it, change it, modify it, set it, right? It's not just one variable. You are also removing a lot of instructions for processing that variable. Make sense? So in one shot, you are reducing space. Space reduction is not a big deal, but the time reduction is, right? Okay, so we can remove that head reference, right? Head pointer is not required. We will just have tail. And as I said earlier, tail reference, if you just have it, it's kind of, so there is something called Occam's razor. it's a principle, idea called Occam's razor in physical sciences. The idea is, if a theory, suppose there are two theories, theory 1 and theory 2. Suppose the requirements here are, say, A, B, C. The requirements here are A, B, C, D, E, F, G, H, I, J, K. Both theories are explaining the world using some of these assumptions or some constraints like this. Then Occam's razor says that better choose this theory over this. It's very likely that simplicity, right? I mean, if you can get away with some variables, constraints, resources in defining something, do that, right? That is Occam's razor in physical sciences. So similarly, I mean, we have a model where we can get away with head, and it is simplistic model. It reduces space, it reduces time, then follow that, right? So that's the idea here. Okay, so this implementation is superior. Superior, it does not asymptotically improve the complexity, but practical improvement, okay? There is no asymptotic improvement. I mean, you won't reduce the complexity from n to 1, n to log n, or anything like that. But maybe in some instructions, you are reducing a couple of instructions, and rotate function is so fundamental, right, to a lot of applications. It realistically models all these situations, scenarios, all these applications, which have this feedback loop and so on. Okay, rotate operations. Let's see. What do you mean by rotate operation? So let's consider the CLL, circularly linked list. This is your tail. This is your tail, right? If this is the tail, you can automatically find the head pointer. How? Tail.getNext is the head pointer or the head node. You are not saving the head pointer here, but you can find the head pointer using the tail, right? Hence, you see this dotted dashed arrow, right? Head is not present, but you can compute head if required. Okay, so what is the rotate function? Rotate function means that suppose this is the first node, you process it and add it as the last node. That's the meaning of rotate, right? Now let's do a rotate function. So the first node was LAX. Now after the rotate, the last node should be LAX. How do you rotate? If you just do tail is equal to tail.next, you are done. You're done. See, dead simple, right? So what did we have before? So initially we had remove first and then L dot add last, right? Rotate was this if you just use SLL to implement rotate. Think about it. Remove first itself had a lot of instructions. Add last had a lot of instructions, and you were doing this again and again. But it's unnecessary, right? With this implementation, you just require one line. Tail is equal to tail.next. LX was the first node. When you do this, LX is automatically the last node. Beautiful, right? See, 7 to 8 lines of instructions, or maybe more, has been reduced to just one line. Okay, so it's not asymptotic improvement, as I said earlier, but it is still practically it is useful, right? Because you'll be calling this rotate multiple times, several times. So a decent amount of time you'll be saving. Inserting element at head. Rotate is fine. What about the 3 or 4 other functions? Insert at first, insert at last, delete at first, delete at last. Can we also solve all those problems? Let's see. how do you insert a node at the head? This was the head node. Now we want to insert a new node. Let's create a new node. STL is our new node. So what do you do? So look at the idea here. The next pointer of the new node will point to the head node. Right? The next pointer of the new node will point to the head node. The next pointer of the tail node will point to the new node. That's it. So initially it was like this. We are removing this link and trying to give it like this. Right? So instead of this one link, we have two links. This link and this link. Done. Make sense? So does this make sense? Inserting a node at the head position in a circularly linked list.
Yeah, so just so I'm clear, so what the first thing you do is set newest equal to tail.next, and then set tail.next equal to newest.
Right. That's it.
Okay.
Right. So create the node newest.next next is equal to tail.next, and then tail.next is equal to newest. Okay, so let's look at the implementation. Circularly linked list, everything else remains the same, right? So the structure and all remains. You have access methods, you have update methods, you just have the new function, rotate function, because we saw that it's fundamental to the circular list. Okay, you can also have remove last, not shown here. Okay, for getting the first node, getting the last node is still easy. What is the first node? Tail.getNext is the first node. Get element, get data or element from it, done. What is the last node? Tail. Tail is the last node. Tail.getElement will get you the data, done. So these are simple. Now let's focus on rotate. See, look at rotate function. So clear, crystal clear, right? Just one line. Tail is equal to tail.getNext. Of course, as I said earlier, for every function, right? For every function, every data structure, you should check for corner cases. Corner cases are, what are the corner cases? Check whether the data structure is empty. Check whether the data structure has one element. Check whether the data structure has two elements. And typically, most of the data structures, you need to have these, check any of these situations. You need to use separate logic, special logic. So here, if the tail points to null, what is the meaning? If the tail points to null, the list is empty. Then you shouldn't do tail is equal to tail.getNext. What happens? What happens if you do that?
Null pointer exception.
Right, you will get null pointer exception, right? So you need to be careful, right? So do all those corner cases checking, right? So if tail not equal to null, then tail is equal to tail.getNext. Okay, now let's see add first. You have CLL, you are adding an element at the first position. First, we will look at the generic case, What is the generic case? So as we said earlier, newest is equal to, so newest points to tail.getNext, right? Newest points to tail.getNext. The next pointer of newest, right, is tail.getNext. next. Tail dot set next is equal to newest. That's it. So these are the two links. This is first link. This is the second link. Tail dot next is equal to newest. Now the previous link is gone. Make sense? Okay, so this we have already covered. And size plus plus, size minus minus, I will not go over this, right? You know, if you're adding, it's size plus plus. If you're subtracting, it's size minus minus. And you cannot subtract or delete from an empty list. Okay, so I will leave all these sentences. Now let's look at a corner case. What is the corner case? Empty list. You have the empty list. That means tail is equal to null. I mean, you can also have this as tail is equal to null or size is equal to 0. Both mean the same. Okay. What happens? You want to add one node, and then that will be the tail. Is that true? The next pointer of it points to the same node. If you have only one node, tail points to the node, and tail dot next points to the same node. So does this make sense? That's your corner case. That's the corner case. Right? What is the complexity here? Still O of 1. O of 1 here, for rotate, O of 1 for add first. I mean, as I said earlier, from SLL to CLL, there is no asymptotic improvement in anything. It's just constant factor improvement. I mean, practically you are seeing the improvement. In the constant factors, you are seeing the improvement, but not asymptotically. Okay. Because it's the same core logic, right? Add last. So this is another beautiful idea. See, add last. Add last is add first, and then tail is equal to tail dot get next. How? Can you tell me how? So this is your tail node, and you have the big list here, right? This is the last node or the tail node. Add first means what? You're adding this as the first node, right? You created this as the first node. Add first of E, let's call it E. And then tail is equal to tail dot get next. When tail is equal to tail dot get next, tail points to this. Make sense? In essence, these two lines make sure that you added a node at the last position. But look at the beauty of this code. What are you calling here? Add last is calling add first. What is this concept called? Code reuse. Right? So when you have modularity, that means different functions are modularized and written as separate functions. You can write the logic of one function making use of the logic of the other function. You don't need to write all the sentences from scratch. I mean, you could have done that. If you wanted, I mean, you could have created a node, I mean, use that create node and do all this changing of links and everything. But that is unnecessary. That's not required. You can reuse the code. So hence we are calling add first and then one more line. So sometimes it is okay, even if it increases by one more instruction, that is fine. But you are getting this code reuse. Why? Because if something changes in the add first logic, it is automatically changed in this add last logic. You don't need to work on two different functions now, right? So code maintenance will be easy. So whenever you're working with, say, millions of lines of code, sometimes it is okay to go away from performance and focus a bit more on code reuse, because the maintainability will be huge. With maintainability, that means you're also reducing the cost for development or updation and all, right? So it's kind of the trade-off between performance and cost. If you want to get the biggest performance, you need to individually write each and every line of code. But the cost, that means you need to update different regions of code base, right? So it's kind of a trade-off between performance and cost. Next, remove first. So what is the idea here? So what is the idea here? This is the tail node. This is the tail node. You have the circular linked list. Suppose this is the head. And this is the second node, right? First node, this is the second. What do you mean by removing first? That means you're deleting this, right? You're deleting this. How do you do this? Tail.setNext is equal to head.getNext. This is the core logic. Tail.setNext, tail.next should directly point to the node after the head node. Right? Instead of these two links, you have this one link to directly access it. That means you're deleting the first node. That's the meaning. This is the core logic. Tail.setNext, right, is head.getNext, but you would be saving head. I mean, it's easier to do it that way, right? Make sense? Okay, what is the corner case? Corner case is this. Suppose head is equal to tail. Can you tell me what do you mean by head is equal to tail?
So if the list is only of size 1, then the head is the tail because there's only one element that's linked to itself. And so if you're removing that first element, then you're removing all the elements. So there should be an empty list left over.
Very good. Head is equal to tail. That means there is only one node, and you're removing that, you're setting tail is equal to none. But head is equal to tail can also happen if both are pointing to null, isn't it? It's not necessary that the list should have only one node. Even if they have 0 nodes, still head is equal to tail, isn't it?
Yeah, but that case isn't going to happen because it has an is empty at first.
Exactly, right? So though head is equal to tail happens in 2 situations, you're already covering one of the situations. So the only possible alternative situation is this, right? There is one node. So instead of head is equal to null, you can also write it as if size is equal to 1. Can you do that? If size is equal to 1, can we write it like that?
What, the head equals tail?
Yeah, instead of head is equal to tail, can we write size is equal to 1? Right? What do you think?
No,
Why not?
because what if that one, actually, I don't know. My first thought was that, well, if it has size 1, that means it has a non-null object. So then actually it should, I think it should.
Right. So it should work. right? It should work. So it is better to write it like that. If size is equal, I mean, it is better to write it as size is equal to 1 instead of head is equal to tail. Because as I said here, right, head is equal to tail can happen in 2 situations, but in some other problem there, I mean, you are working with in some other software, the same condition might have 2 different situations. One of them is not already taken care of. Hence, try to use simpler way of giving the same condition, right? So here, simpler way would be size is equal to 1. Now there is no confusion, right? It's easier to analyze also, right? If it is like this. But
I have a quick question.
both of these, work. Yeah.
Yeah, quick question. I might be missing it, but I don't see where we set the new head of the list after we remove the first element or the first node.
So remember, there is no head node for a circularly linked list.
Yeah, that was what I thought, but they still use like the head and tail terminology for the code block, so I guess I was kind of wrapped up on that.
Oh, where?
Oh, like, well, you use head and tail in these code blocks.
Oh, here, see, as I said, this head is only being used in this function.
I gotcha. Okay.
See, head is not the pointer or the node or the variable created in the circularly linked list class. See, we are defining for the first time here. But did we define tail? No, we did not define tail here because tail is already a part of the CLL data structure. Head is not the part of CLL data structure.
Yeah.
I mean, for ease of use, we are creating head here.
Okay, yeah, that makes sense. I was thinking SLL that it still had a head. Thank you.
Right? Okay. Next, let's move to DLL, doubly linked list. Now, can you tell me the quick differences between CLL and SLL?
DLL points backwards as well as forwards.
Okay, let's say SLL and CLL, circular.
Oh, DLL, I'm sorry. Between SLL and CLL?
Yes. So you know some situations where you would prefer CLL over SLL. Is there any situation where you would prefer SLL over CLL?
Well, when the process isn't repeated, you wouldn't want to use CLL, right? If it's like a one and done, there's no point in rotating them.
Oh, okay. Repeat again.
I'm sorry, say that again?
See, I mean, there are applications where CLL is better than SLL. Are there applications where SLL is better than CLL? Or why would you need SLL and not CLL? Okay, so think about it, right? I mean, we are trying to compare, pros and cons of data structures and why you want to use one data structure over the other. Okay, so doubly linked list. It's very similar to your singly linked list. The only change is you have the previous pointer, right? You have the previous pointer. So look at all the previous pointers, right? So that's the major change. And you can implement DLL in many different ways. The authors of our textbook, data structures textbook, gave a very beautiful way to implement DLL. I mean, it can be implemented in many different ways, but they use sentinels called header and trailer. This is not the only way to implement DLL, okay? So some people consider this as head and tail and all, right? but the authors use this sentinels. That means these header and trailer do not store data, right? They do not store data. Data is not stored here. They are just present there. That's it, right? As a starting point. They do not store it. Compare it with the head node of SLL. Head node was saving data, storing data. Tail node was storing data, but here header and trailer do not store data. Okay, why do we need this? I mean, isn't it, I mean, are we increasing this by say 2 nodes, extra space, right? But here they say that we can, I mean, if we use these sentinels, we can code the insertions and deletions in a unified manner. It's a very beautiful way, right? So we will cover that later. It's a very beautiful way, unified manner, very powerful way of writing it in a very generalized way. So I love this implementation over the implementations of many other, textbooks. So you will see that. So we'll just cover 1 or 2 slides and probably then we'll stop. Okay. So inserting at a node, think about inserting at a node. What do you need? You need the predecessor, the way we are going to insert at a node, right? In a unified manner is like this. You will have a predecessor, you will have a successor. Between those two, you will insert a node, right? When you're inserting a node, you know that automatically the 2 pointers from the node should point to predecessor and successor. But what about the pointers in predecessors and successors? They were pointing to like this, right? Predecessor was pointing to successor and vice versa. You just need to change them to point to this new node. Done. Right? So inserting at arbitrary location is same as inserting at the front location. In the reasoning wise, see, what is the predecessor? Predecessor is the header, successor is the first node, and the inserting here happens exactly like before. You just give the predecessor and successor, it's the same logic. What about inserting at the end? It's the same logic, right? Inserting at the end is between trailer and a previous node of trailer. So creating one function called add between or insert a node between 2 successive nodes, you can code all these things in a unified manner, inserting at front, inserting at the last, inserting at a particular location, right? So similarly, deleting a node, right, at the front, at the end, in the middle position can be handled in a unified manner. Okay, we will stop here. We will continue in the next session. So any questions, team?